Max. I'm an ex-bootneck who, many of you, has a bit of experience in the InfoSec industry as well. And this evening, I'm going to introduce you to Linux heap exploitation. The materials from like the first hour or so of a course I teach, both online and at conferences, at least pre-pandemic when InfoSec conferences were actually running. And we're going to operate sort of like a workshop, basically. That means if you fancy, you can just watch and listen. Or if you were able to get in the Slack channel and download some of that material and follow the instructions to set up like an Ubuntu VM with a couple of those tools, the Pwn bag and Pwn tools Python frameworks, then you'll be able to follow along and write a little exploit with me. Nothing serious, just a few lines of Python. Yeah, so I've kind of messed with the order of this, so I'm flying by the seat of my pants a little bit. So if everything's a little bit out of order and all over the joint, and I skip a lot of slides, then I do apologise for that. If you've got a couple of monitors and you are following along, that'll be the best setup. Probably easy to have like me chatting away on one, because I'm going to be showing you some of my screen, that Ubuntu VM that I was talking about, and then you can have your other stuff on another monitor. Apologies, that's just popped into my head just now, and I didn't write it in the Slack channel. So it might be a little bit awkward following along with this stuff, but we'll take our time with it and see what we can do. So we're doing a bit of Linux heap exploitation. When I say Linux heap exploitation, I actually mean specifically something called glibc heap exploitation. And we're going to start by learning what on earth glibc is. Then we're going to learn a bit about heaps and how they work. And then we're going to wrap things up by exploiting a small vulnerable binary using a heap exploitation technique. So glibc stands for the GNU C library. GNU is in the recursive acronym GNU's not Unix. Read Linux. I know some people would get very upset with me for saying that, but Linux for all intents and purposes. And C is in the C programming language. So essentially like the Linux C library, basically. Most programming languages have what's termed a standard library, which is just a collection of useful code, like boilerplate code, for developers to use when they're coding in that language. And glibc is just one implementation of the C language standard library. And all it does is provide a bunch of boilerplate functionality, things like functions like memcopy, printf, fopen, all that basic boilerplate stuff that you've probably used if you've been programming in the C language. And it provides that functionality to not only programs written in C, but C++, and by extension, higher level languages like Python, whose interpreters are often written in C. So glibc is just one implementation of the C standard library. There are a bunch of others. I'm sure you guys know, for example, that Android uses a modified version of glibc called Bionic. And if you do a lot of embedded stuff, you might have also come across things like UClibc and Muscle and all that good stuff. So glibc is just one example of a Linux C standard library. And the reason we're interested in glibc specifically, rather than Muscle and UClibc and Bionic and all that good stuff, is a couple of reasons, really. The first is that glibc has been knocking around for almost, getting on for 30 years now. It's a very mature implementation, and that has made it very prolific. It is everywhere. Most desktop Linux distributions use glibc as their C standard library, including a ton of embedded distros as well. All the popular ones like Ubuntu, Debian, Arch Linux, to name just a few. So simply put, like glibc is more or less, you can find it everywhere. If you're messing with Linux desktop distros, then glibc is the way to go, basically. The second reason is that because it's quite a mature implementation, it has the best, or some of, if not the most protected internal implementations, especially its heap. So if you're learning glibc heap exploitation stuff, your knowledge is reasonably transferable, because if you learn how to exploit the glibc heap implementation, if you find a heap bug in programs that are using other implementations, like other heap implementations or other C library implementations, chances are they won't be using half as many, if any, exploit mitigations as glibc was. So it was probably more difficult in glibc to get your exploit working. And then after that, you know, you want to get it working on Android against Bionic, then it'll be much easier, basically. So to sort of hammer home this point about like how prolific and how important glibc is to the sort of everyday running of a Linux distro, like Linux desktop distro, I'm going to use my Ubuntu VM here. This is an Ubuntu 18.04 long-term support distro, like you guys have. Someone just use voice to check with me that this is, you can see this and this is legible, please.
Yeah, looks great.
Yeah, excellent.
I can increase the font size if need be. So those of you who downloaded the material from the Slack channel will have like a heap lab _ DC441905 folder that was a tar.gzip. Hopefully you've unzipped that, untarred it, and this is what will be in there. For the rest of you, don't worry about that. There is the heap lab glibc heap exploitation PDF in there. We're not going to be making much use of that right now, but it's a PDF that I distribute when I'm teaching these courses. It's got like a ton of heap internals stuff, a lot of which you'll see like online, but maybe there's a bit of errata on there, or you know, people don't dig quite as deep into it. So if you want to learn a bit of heap internal stuff, then hopefully that PDF will help. And it's got like an overview of a bunch of the different heap exploitation techniques that, you know, there's they've got a bit of overlap, but there's at least like 13 of them knocking around. And today we're going to learn one called the House of Force, which we'll get onto shortly. So bear with me. So I'm going to use LDD. You don't have to follow along with this, even if you have your VM set up. This is just, like I say, a bit of a demonstration to prove what the deal with glibc is. So LDD is short for list dynamic dependencies, right? So you can run that on more or less any program on this system, and it's going to dump all of the shared objects that a specific program relies upon. I run it here against ls just to show that, you know, any old Linux program will work here. And it dumps a bunch of these different like .so files. So a .so is short for shared object, and they are the Linux equivalent of a DLL, basically. And glibc manifests, as most libraries do, as one of these .so files. Specifically, libc.so.6. This is the glibc shared object. Glibc is often shortened to just libc.so, as I said, shared object. And .6 is it's the Linux ABI numbering system. So basically, if you're a maintainer of a Linux library, like libc or any of these other ones that we can see here, like libse Linux, libdl, libpthread, all that good stuff, you can see that they've all got these numbers appended to the end of them. So if you're a Linux library maintainer, then every time you change your ABI, every time you change the way programs have to interact with your library, you have to increment that value. libc is at 6, or glibc is at 6 right now, because back in the day, the Linux kernel maintainers actually forked their own version of glibc. And people used that up until, I think, ABI version 5. And then the original glibc maintainers added a bunch of features and functionality that meant people started using the original fork, the original version of glibc again. That was ABI version 6. And then since then, it's more or less stayed as 6. Backwards compatibility is very important when it comes to things like C libraries. So you're unlikely to see anything other than libc.so.6 nowadays. Excuse me. So I am just going to run the file command on this. What do I want to do? Third one. And we'll see what exactly the libc.so.6 file is. And it turns out it's just a symbolic link to another file called libc-2.27.so. So libc.so.6 is just the symlink. That's going to be the case on most systems. You'll have a symlink to the actual glibc binary. That has a different version number in it. This is actually the one we're interested in. It's different to the ABI version. Like I said, you're unlikely to come across anything other than .6 in that case. 2.27 is the glibc version. Now, glibc actually has a pretty aggressive release schedule. I think they release a version once every 6 months. So 2.27, we're on 2.31 right now, I believe, with 2.3 coming at some stage later this year. But you you're unlikely to see the very latest cutting edge versions. Typically, a distro like this, Ubuntu 18.04 long-term support, will be born, as it were, with a specific version, in fact, a specific binary, a specific glibc version and binary that won't change throughout its lifetime. Even though there have been more subversions of Ubuntu 18.04, I think you get Ubuntu 18.04.1, .2, they all have this exact same libc binary, not only the same version, the exact same one. And that's to guarantee that if anything changes in libc, they don't break things in user space when people update their versions of Ubuntu, for example. So if we run a file against that, we can see that it is just a 64-bit ELF file. So much like how much like how Windows DLLs are PE files, just like executables, on Linux, the shared objects, DLLs as it were, are ELF files as well. And there's a build ID here as well, this build ID value, that can help you specify, that can help you find a very specific an actual binary, basically. So this build ID, and you'll notice that build ID, which identifies this specific binary, not just this version, but this specific build of glibc, will be the same throughout Ubuntu, like any Ubuntu 18.04 distros, no matter like what subversion they are, no matter when you downloaded them, how up to date they are. So that's the nice thing about like this, the way, I guess that's not a great thing, a cutting edge distro, a bleeding edge distro, as I should say, like Arch Linux will update their versions of glibc. If you download like the very latest version of Arch Linux right now and update it, you might see that it's got, excuse me, glibc version 2.31, the very latest. So you can actually run your versions of glibc, and they will spit out a little bit of information. So if you're CTFing or anything like that, and you're sort of curious as to what version of glibc you're using, you could just run it. You can run that binary, and it will spit out a bunch of this version information, tell you which version of glibc it is, tell you which version of GCC compiled it, etc., and all that good stuff. So that's our little glibc shared object. It's version 2.27, and that's important for exploit developers because we know, once we know the glibc version, we know what exploit mitigations are going to be employed in that version of glibc. So if I use du for disk usage on that binary, I hope this hasn't gone off the bottom of anyone's screen, just say if it has. We can see that this glibc binary is 2 meg, which is pretty small, to be honest. Obviously it's stripped, hasn't got any debug symbols and whatnot, but how important can a little 2 megabyte binary be to the integrity of an entire Linux desktop? Well, I'm going to find out by deleting it. If you have been following along with your VM, don't do this part. I'll say that again. Don't use the following command, all right? Excuse me. So I am going to delete that shared object. In fact, I haven't even deleted the shared object, you might have noticed. I just deleted the symlink, right? So that libc.so.6 file is gone. So libc-2.27.so is still on the system, but programs aren't going to be able to find it. And you can see immediately when I start using basic programs like ls to list directories, who am I to see my username, they start kicking out this error message that says libc.so.6, can't find it. So immediately, even basic functionality on this system is hosed by deleting that one symlink. That's how important glibc is. Even programs that are like listing directories and doing very basic stuff are all using that glibc functionality. So if I try and use stuff like Python, or sorry, Python 3 on this system, again, like, you know, Python isn't like a C program or anything, but the interpreter is written in C. Python 3 is hosed. If I'm dumb enough to close my terminal, best of luck getting that back open. That's not going to work. Graphical user interface stuff like Firefox, I'm clicking here in the bottom left. No chance, that's hosed. I can try and shut this system down, and it will attempt to, like it'll get this far, and you can see we've got a few nasty failures going on there. It ain't going to get much further than this, basically. I can even, I don't know whether you guys can see what I'm doing here at the top, but I mean, I can attempt to power this thing off. Yeah, and it won't even respond to hypervisor commands at this point. It's hosed basically. So that's glibc. That's how important like the C standard library is to your average Linux distro. Excellent. So, all right. So included in that boilerplate code that glibc provides is a dynamic memory allocator known as Malloc. And dynamic memory allocators are used when a program can't know the size or number of objects it needs prior to runtime. And I'm sure you guys are all familiar with the concept of like a stack in terms of like memory management and how that works. Stacks are fast because they're backed by registers, but they don't deal particularly well with large memory requests. They don't deal well with dynamically resized memory requests, and they don't deal well with recycling data, recycling memory very efficiently. And that's where memory allocators like Malloc are dead useful. They may be slower because they're implemented in software, but like I say, they deal with recycling and resizing and large allocations much, much better than the stack. Oddly enough, you can make dynamic allocations from the stack using functions like alloc-a or alloc-a, some folk call it, but it's generally frowned upon in the Linux community. Like I think the Linux kernel went dynamic stack allocation free like a couple of years back. It's like I said, it's frowned upon for a couple of reasons. So all Malloc does is dish out these so-called chunks of memory to programs at runtime. And those chunks come from large contiguous blocks of memory known as heaps, right? So if you've ever dealt with strings in C, you've almost certainly used Malloc. In C++, you're a little more abstracted. The new and delete operators are just thin wrappers around Malloc. As are by extension things like make shared, make unique, all that good stuff. And those chunks, and those that Malloc use, I should say, is again like very prolific. So not only is glibc extremely prolific, and especially on any given system, it's used in basically every binary on there. We saw even Python and Firefox and all that good stuff didn't work when we removed access to it. But Malloc is also extremely prolific. Even if your code doesn't explicitly invoke Malloc, chances are one of the library functions you're using does. Basic functionality like opening a file, dealing with I/O, starting a new thread, all use Malloc under the hood. So you'd be hard pressed to find a binary that doesn't use Malloc on your system. Only the very simplest programs aren't going to use Malloc for anything. And like I said, even if you look at their symbols, their imported symbols, and they don't use Malloc or one of the collection of functions that Malloc belongs to, excuse me, that doesn't necessarily mean that one of the other library functions they're using to get what they're doing done doesn't use Malloc in the first place. So Malloc itself is it's like an umbrella term basically for a collection of functions and metadata for the purpose of, like I said, dishing out those chunks of heap memory to processes. And to help us visualize how Malloc works, we're going to debug a small demo binary. Now, there's two primary Malloc functions. As I said, it is an umbrella term for a bunch of functionality, but we're concerned with just two of those functions. So Malloc itself, bear with me, I said I was going to skip some stuff. So Malloc itself is used for requesting heap memory, and free is used for recycling it. We're not going to look at free today, we're just going to look at Malloc. And it is a little confusing to have a function called Malloc that's used to request heap memory from the dynamic memory allocator, also called Malloc. I understand that, but at least it's a simple function. It takes a single argument, the size in bytes of memory that you want, and it returns a pointer to that amount of memory or slightly more for you to do with as you wish. So we're going to, as I said, debug a small demo binary. So if you are following along, then you should be able to navigate to the heaplab DC441905 directory, and from there navigate to the house of force directory, in which you'll see like a collection of binaries and Python scripts. And we're going to start by debugging the demo binary under GDB with the command gdb demo. Once GDB has started, we're going to set a breakpoint on the main function with break main, which can be shortened to just b main. And then we're going to run the program with run or just R. And part of the instructions when you were setting up these VMs was to install a Python framework called Pwnbag. And it's just, Pwnbag is it's a Python framework for exploit development that makes GDB usable, basically. And this here is Pwnbag. There's a lot going on the screen, but we're only concerned with the source panel here, this source brackets code panel, third from the bottom, and in which we can see exactly what this program does. This is a bit of C code here, and we can see that all it does is use the malloc function to request different varying amounts of heap memory from the malloc memory allocator a bunch of times. That's all it does. It doesn't actually do anything. It just requests that memory and then quits. Starting with this first request here on line 5 for 9 bytes, which is just an arbitrary value. And it's going to store the return value from that call in a variable called a. So before we let it do that, we're going to look at the heap. So the vmmap command can be used to inspect this process's virtual address map. And we can see from the legend at the top that the heap should be colored blue, but there isn't any blue text in the vmmap command output. And that's because malloc won't request heap memory from the kernel to form a heap until it's actually needed. So we're going to execute that first request to malloc for 9 bytes using the next command, which can be shortened to just n. Incidentally, if some of your Pwnbag output looks a little bit different to mine, Pwnbag's updated, with pull requests like every day, every week. So functionality changes. Its open source functionality breaks very often. So I make no apologies for that, I'm afraid. Like, if you're using a different version to me, then we'll just have to make do. So you can see that execution has progressed to line 7 here, indicated by this arrow. That means we've executed that first request to malloc for 9 bytes. So if we use the vmmap command again, we can see that now we have a heap at address hex 602000, and that it's about hex 21000 bytes long. That's about 135,000 bytes. And we can inspect that heap memory using the Pwnbag command viz heap chunks. And you can just shorten that to viz. And I'll do my best to explain what you're seeing here. In fact, what I'll do is I'll clear the screen and show you just that. So this area colored, I want to say cyan, green, these 3 quad words here, they're that first chunk. That is the chunk, that's the user data of the chunk, I should say, or all of this green area. Your colors may differ depending on what terminal color output you have set up. But these 4 green or cyan quad words, that's the first chunk. That's the chunk that was returned by that first request to malloc for 9 bytes. And we can confirm that using PA or print A to print the return address from that first request to malloc, which gives us the address hex 602010, which is this value here. And that points to the first quad word of so-called user data of this chunk. Chunks are split up into metadata and user data, and user data is what the user or the program has to mess around with, to write into. So the first thing you'll notice is that we got more than 9 bytes, 24 bytes, 3 quad words at 24 bytes to be precise, these 3 quad words here. The reason for that is that that is just the minimum chunk size that malloc will ever give you. If we use the next command again to make this request here for just 1 byte, the viz command shows us that we got a second chunk on the same heap, this pink one, or this purple one, I guess, with, again, 3 quad words of user data. So even if we use next again to request 0 bytes from malloc, viz reveals that, once again, we get a minimum size chunk. So any request between 1 and 24 bytes will give us that minimum sized chunk with 24 bytes of user data. You might also be wondering what this value here is. These values, they're part of the same chunk, or they're part of their separate chunks that are delimited by these colors, but they sit before the user data. Well, Malloc uses so-called inline metadata, which means much like how the stack keeps some of its stack metadata on the stack itself, like say base pointers and return addresses, the heap keeps a lot of its metadata inline as well. I'm getting harassed by a pet. So in this case, the heap has a size field kept inline here. Every chunk has a size field, these three values here, and they indicate the sum total of bytes that make up the chunk, including the size field itself. So in this case, 24 bytes of user data plus 8 for the size field, because we're on a 64-bit architecture, gives us 32 or hex 20 bytes. But we're seeing hex 21 values here. The reason for that is that chunk sizes increase in increments of 16 bytes. And that means if we use next to request exactly 24 bytes of heap memory, Viz shows us that we got a minimum size chunk with 24 bytes of user data. But if we use next to request 25 bytes of user data, Viz shows us that we got the next chunk size up, hex 31, with 40 bytes of user data. The chunk sizes will increase in those 16-byte increments, so you'll only ever see chunk sizes of 20, 30, 40, 50, 60, etc. And that leaves that low-order nibble, those low-order 4 bits, free to be used for, well, whatever the Malloc maintainers want. In this case, they're used to indicate flags. In the case of all of our chunks on this heap, the prev in use bit is set the least significant bit, indicating the prev in use flag. And that simply means that the previous chunk, the adjacent chunk in lower memory, so the previous chunk to this purple one is this green one here, it means that previous chunk is in use, as in it hasn't been freed, it hasn't been recycled yet. Since all of our chunks are in use, all of them have their prev in use bits set. So you might also be wondering why the first chunk didn't start here at the beginning of this heap at address hex 602000. It started one quad word after that, leaving this kind of offset pattern down the heap where we've got these size fields on the right-hand side here, followed by the user data. And technically, that chunk does start there. Malloc chunk shapes, at least when viewed like this, are variable, and they depend on a couple of factors, including the size of the chunk, and whether that chunk is free or not, the size of the previous chunk, and whether that chunk is free, or the size of the adjacent chunks, I should say. And in fact, in the Malloc source code, alongside the chunk struct definition, there is in fact a comment that just says this chunk struct definition is misleading, but necessary. So fortunately for us in this technique, we're not going to be dealing with free chunks. We're just going to see this kind of offset pattern here, where we start with a size field on the right-hand side, followed by 3 or more quad words of user data. So lastly, I'd like to draw your attention to this region labeled the top chunk by Pwnbag here. And you'll recall from the output of our vmmap command a moment ago that this heap is about 135,000 bytes long. But the viz command is only showing us like perhaps between 100 and 200 bytes of that here. The rest of that as yet unused heap memory is considered one large chunk by Malloc, that it calls the top chunk. And every time we request memory from Malloc, it breaks off a piece of that top chunk and gives it a size field, and then gives it to us, gives it to the program. So if we requested 16 bytes using the Malloc function, we get a 24-byte or hex 20 sized chunk with the prev in use flag set. And every time we request more memory from Malloc like this, at least if we're not freeing memory, Malloc will just keep breaking off chunks from the top chunk, giving them a size field, and then giving them to our program in the form of a pointer to their user data. And Malloc is deterministic. These aren't random. It will just keep doing this, and the top chunk will keep shrinking every time we make these requests until the top chunk isn't large enough to satisfy those requests, at which point Malloc will attempt to replenish the top chunk. And like all of the other chunks that we've seen so far, the top chunk also gets a size field, and that's so Malloc can keep track of it, or how large the remaining memory in the top chunk is, I should say, so that it knows how close it is to exhaustion. And interestingly enough, that top chunk size field, at least in the version of glibc we're going to be targeting today, has no integrity checks surrounding it. So Malloc will take that value as gospel. And that forms the basis of the technique we're about to look at, the house force. So if you've been following along, you can Control V or quit out of GDB. And we're going to take a look at our first vulnerable binary. It's the house of force program here. You can run yours on the command line. I'm just going to run mine under GDB. If you're running it under GDB, don't worry about setting breakpoints. You can just run it with run or R. And I'll start by explaining a little bit about what's going to happen. So the house of force is the name of the binary, and that's the name of the technique we're going to cover. Heap exploitation techniques have these weird kind of names a lot of the time. Back in 2005, someone using the handle Phantasmagoria published something called the Malloc Maleficarum, which described 5 novel heap exploitation techniques, novel at the time, that they called the houses of prime, mind, force, law, and spirit. And at least 3 of those are still viable today, including the house of force. They weren't the original heap exploitation techniques. The first so-called generic heap exploitation technique was done by a chap called Alexander Pesliak, aka Solar Designer, back in the year 2000. I think he pwned, I want to say, the Netscape browser. This was back in the day when the Windows and Linux heap implementations weren't so different. And since then, the Windows heap implementation has had a lot more security improvements than the Linux one. Linux one is often, as Linux security is generally a few years behind commercial platforms like Windows. Incidentally, if you've not heard of Solar Designer, he's a dead interesting bloke. He not only created the original, or developed the original heap exploitation technique, the unsafe unlink, which you may have heard of, but he also is the father of ROP, return-oriented programming. Like back in '97, in the wake of Aleph-1's smashing the stack of Fun and Profit the previous year, he developed the first non-executable stack patch for the Linux kernel, like years before it even actually became mainstream, to stop those JMP ESP attacks and all that good stuff. And then he bypassed his patch by developing return-oriented programming, or retlibc. And then he actually went on the next year to develop a patch for his bypass for his patch that mapped libraries into addresses with null bytes in them, so they couldn't be used in like rogue string overflows and all that good stuff with ROP. He's a dead interesting guy. If you want to read more about him, Frack did a great interview with him in 2016 that you can still read online. He's proper old school hacker, listening to Western radio through the jamming in Russia in like the 80s or whatever. Anyway, so after him came these 5 generic heap exploitation techniques. And when I say generic, I mean, say you were to an overflow on the heap can occur just like an overflow on the stack, right? That concept is the same. It's just an overflow in memory, as it were. One bit of memory writing into another bit of memory that it shouldn't do. And overwriting a function pointer, for example, on the heap is not really any different to overwriting a function pointer on the stack. That's, I guess you could technically call that like a heap exploit. But the idea of generic heap exploitation techniques are that they take advantage of the heap implementation itself to deny a service, code execution, arbitrary read, write, whatever. And that's what the idea is with the techniques I teach, including the house of force. It is a so-called generic heap exploitation technique. So before we run this binary, actually, I'm just going to close GDB again, and we're going to run checksec. We're going to run a command called checksec against this house of force binary. And checksec, you probably come across that if you do any Linux exploit dev. It'll be installed if you install the Pwn Tools framework as well. And it just dumps a few protections that this binary has. So we can see this one is a 64-bit ELF binary. It's compiled with full railroad. We won't dig into railroad too much. Basically, programs can be compiled with no railrow, partial railrow, or full railrow. Partial railrow just rearranges some of the sections, the data sections within a binary to avoid overflows from like the data sections and the BSS sections that users might be able to control from overwriting important stuff like .plt sections and all that. Full railrow is a bit more of a modern implementation. That marks sections like the .plt and the .fini array sections as read only after initialization. So if you've done any sort of Linux exploitation, you might have, if you've managed to contrive like an arbitrary write, you might have overwritten like a .plt entry so that when that function is resolved, execution goes where you want it to go as an attacker rather than where the program wants it to go. So in full railroad programs, you can't do that stuff. It takes away our ability to do overwrite stuff in the program, even if we know the address of the program. Stack canaries and NX, because it's 2020. This program is not position independent. That isn't necessarily a prerequisite for heap exploitation, but it just allows us to overwrite a specific target. What we're going to do with this binary is it's got a bug, and we're going to leverage that bug for our House of Force heap exploitation technique. And we're going to start by leveraging it for an arbitrary write. So we're going to write our data somewhere where we can see that we've written our data, because arbitrary writes are a really nice, strong primitive to start with. If you can forge an arbitrary write, you're well on your way to getting code execution or doing whatever you want, basically. And this run path value is irrelevant. Like it says it in red because a run path like this normally would be bad. Run path is just where is this binary going to look for its shared objects like glibc. Typically that would just be where the system tells it to, right? Which would be a directory that users couldn't mess with. In this case, it's using a specific directory in this directory tree that I distributed to you guys in that tar.gzip file, because I'm linking it against a different version of glibc than whatever one you have on your distro. So that's the interesting thing about glibc heap exploitation, is that just because a program isn't vulnerable on one distribution, if you're taking advantage of something like a heap bug, it doesn't mean it's not vulnerable on another one, because of course the heap implementation will be different. Even though the program is identical between, say, like, Ubuntu 18.04 and Ubuntu 20.04, whatever the latest version is, maybe it's not exploitable on 20.04, but if someone's running that same binary with the same bug on Ubuntu 18.04, it may be vulnerable because that version of glibc is different. What I've done here is forcibly run it against a specific version of glibc, actually a slightly more up-to-date one than the one we're using on this system, glibc 2.28. And you'll notice there's no tcache extension. I've modified it slightly so that we're not going to see a bunch of extra stuff appear on the heap. The tcache is part of like modern heap implementations. It actually makes things easier to exploit rather than harder. So not having the tcache is just going to make things a little less messy when we're inspecting the heap. Don't think that I've modified it to make things easier or anything like that. It's just that I've compiled it with a flag that says something called no experimental malloc. If anything, this would potentially be easier to exploit with the tcache. Like I say, it's just to clean things up. So this House of Force binary is it's a small CTF style binary written in C. It has a heap bug that we're going to leverage the House of Force technique against to, like I said, get an arbitrary write and then eventually, hopefully, if we have time, code execution. I'll just check with the likes of Joel and whatnot, because I can't see anyone's screen or anything or any chat. How is everything still? Can you hear me? Can you see me?
Yep, everything's working correctly. It's great.
Yep, cracking. Thank you very much. Okay, so like I said, I'm going to run that on the GDB, and then I'm going to use the run command to start it up. So it prints this little splash screen here. And then after that, it prints a couple of addresses. These are leaks. Now it prints puts, which is a glibc function. So it leaks libc and it leaks the heap. All right, yeah, not very realistic. What's the point in having ASLR if we're just going to leak that stuff? These binaries are going to leak these addresses so that we can focus on the technique at hand. Not all of these techniques require leaks. They don't all necessarily require leaks. A lot of them do. If you're exploiting modern binaries, as I'm sure you're aware, you probably need some kind of info leak. When I teach this course, I normally have a bunch of challenges and stuff where once you've learned a technique, you then have to leverage that heap corruption bug to leak libc and heap addresses, which you can do via heap corruption as well. So even just with one heap bug, you don't necessarily need to have like a separate info leak bug. You can turn heap bugs into info leak bugs and then subsequently use them to get code execution or denial of service, whatever you want. That's what's so fascinating about heap exploitation for me. Like I said, in this case, it's leaking libc and it's leaking the heap just so we can focus on the technique at hand without like trying to contrive a leak and have to explain all of that stuff. So underneath that is just a little numbered menu. Like I said, this is a CTF style binary, and option 1 allows us to just directly request chunks of memory from Malloc. So if I pick option 1 and press return, it'll prompt me for a size. I can say 24 bytes, and then it'll prompt me for some data that I can write, that it will then subsequently write into that chunk's user data. And you can see we can request up to 4 chunks with this binary. There's no pretense that this binary is anything realistic. Like, it just gives us an interface directly to Malloc. Maybe you can just make arbitrary requests to Malloc like this. I've seen enough black box network protocols where values over the network are just passed into Malloc or string functions to know that it's not necessarily that unrealistic. But having done that, I can break in GDB with Control-C, and then I can just use the viz command as normal to inspect heap memory. And as expected, when I requested 24 bytes of user data, I got a 20 sized chunk with the prev in use bit set, or the prev in use flag set. And then my 3 quad words, my 24 bytes of user data. And we can see those capital Ys that I just wrote into that data represented here on the left by hex 59 ASCII Ys, and then like my new line when I press return 0A at the end there. So this is all expected behavior. This is user data. This is what it's for, holding programs user data that whatever it's decided to write in there. If I hit C or I can write continue or just C and hit return, then it won't print the menu because GDB's sort of eaten that input. So you can just hit return to print the menu. Option 2 allows us to see the target. Now, I mentioned that our objective is to leverage, there's a bug here, we want to leverage it to make an arbitrary write. And that's what the target is. The target is just a collection of these little capital X's that reside in this binary's data section. We've seen that this binary is non-position independent, so we know its address at runtime. The stack and the heap and the library is all randomized, although we have a libc and a heap leak, but in non-position independent binaries, you'll know the address of the binary at runtime. So we know the address of the target. That's why this program isn't position independent. So we can leverage an arbitrary write against a known address to just check that we can, basically. So what I can do is Control-C to break in GDB, and then I can just dump quad DQ. So DQ, sorry, short for dump quad target. And that's the symbol name of the target. And if you are using a more recent version of Pwnbag than I am, there is a bug that got introduced a while back where you can't do that. You need to do dump quad, I think, ampersand target. There's an issue around that, but it'll get fixed shortly enough. And we can see these hex 58s here representing the target, right? Those capital X's. So the idea being that if I continue with C, hit return to print the menu, once we've made our arbitrary write, I should be able to pick option 2 to print the target, which will print that data, print those capital X's, and we should see our own data there instead. So all we're really doing is overwriting like a string in memory. Nothing particularly sexy quite yet, but it just proves that we can make an arbitrary write using our House of Force technique. So normally at this point, I would ask everyone to like have a play with the binary, get familiar with it, mess with GDB, get familiar with the tools and whatnot, and find the bug. Out of interest, has anyone found the bug? No, I'll take that as a no. Out of respect for your time, I'll just tell you now. So if I make a request for a chunk by picking option 1, and then I'm just going to pick an arbitrary size, 24 bytes, so a minimum size chunk, and then I spam a ton of user data in there, much more than 24 bytes, and then hit return. Control-C followed by viz shows us that this is the second chunk that I got. And these hex 59s, these capital Ys are my input here. So I filled up those 24 bytes. And then the remaining 8 bytes overflowed, this time overwriting the top chunk size field. And as I said, that top chunk size field has no integrity checks. You'll notice that even though we've overwritten the top chunk size field, which you'll recall was like hex 20, 10, whatever, the program's still running, right? Nothing bad has happened yet. Like I said, there aren't any integrity checks in glibc version 2.28 and below. 2.29 finally introduced a top chunk size integrity check. And I don't want to give the glibc maintainers shit, because they do, an awesome job like creating the C library for free, and it's a very complicated thing to do. But this technique was introduced, this technique was made public in 2005, and it is a one-line check. There's a one-line check to check that top chunk size. And that wasn't introduced until 2019. So yeah, like I said, understandably, Linux protection stuff can lag a little behind commercial platforms that have all the money to implement them and stuff. So I'm not getting at glibc maintainers. Bugs happen. So this program has an 8-byte overflow that allows us to overwrite the top chunk size field. We can't overwrite the size fields of any other chunks, any inline data, because we have to write when we request. And because we can't free stuff, all we're going to be able to do is overwrite that top chunk size field. Now, we could argue all day over whether that's a realistic bug. It could just as easily be an off by 1 in an array of long integers, right? It's not a particularly egregious overflow. It's one machine word. So like I say, maybe an off by 1 in an array of integers, who knows? Basically, if you have a small overflow on the heap, you may be able to leverage it to overwrite the top chunk size field. And if you can cause a bit of mayhem. So let's consider what we might be able to do if we overwrite the top chunk size field. This on your screen now is like a simplified virtual memory map, much like what we saw with the vmmap command. Typically in x86 Linux, you'll have the applications at the low addresses. No, I'm going to lock my screen if I try and get clever with this. Typically you'll have the applications at the lower address, the application itself, so the binary where our target data is, the lower addresses, often followed by the heap in a region known as the program break. Then a rather large gap, then the libraries, so including libc itself, that libc.so shared object, and then another gap, and then the stack growing upwards. Excuse me. So by leveraging our overflow to corrupt that top chunk size field, we can change the top chunk size field. Now, shrinking it to a small value, I mean, we can do two things with it, right? Like Malloc is going to consider that top chunk size value to be a size field. So we can't do anything clever with it, like writing addresses to it. We can do one or two things. We can make it a very small value, or we can make it a very large value, right? There are techniques that involve making the top chunk a small value, but for the house of force, we're going to make it a very large value. And let's consider what happens when we do that. If we were to set the top chunk size field to a large value, Malloc would think that a top chunk spans this gap between the heap and the libraries and the stack, right? If we replace it with like the largest possible value, all the Fs, right? It was hex 2010, whatever. We replaced it with a very large value. Malloc would think that that top chunk extended way into other mapped memory as well. Like I say, the libraries, including libc, the stack, and all that good stuff. So we could potentially use that situation to then make requests from Malloc that would be serviced from that top chunk that Malloc otherwise wouldn't be able to service. And we can make very large chunks that overlap libraries and the stack and all of that good stuff. Right, so this is our house of force primitive. We're going to overwrite that top chunk size field and then make a very large allocation that we otherwise wouldn't be able to. The only problem we have right now is that we're targeting the application, right? We're targeting that target symbol, those capital X's in the data section of the binary itself. I'm not sure whether you can actually see my mouse flapping around there. You can turn on like a laser pointer, I know, with PowerPoint, but I'm worried I'm going to lock my screen if I do that. So how are we going to get to a lower address, basically, with like a large allocation? Well, we could make a very large request that wraps around the virtual address space back into the application at a lower address than the heap. And this is possible even in even in 64-bit architecture. And that's exactly what we're going to do. We're going to leverage our overflow on the heap to overwrite the top chunk size field with a large value. And that's going to make Malloc think that the top chunk is much, much bigger than it is. It's going to make it think it spans way down through the libraries, through the stack, and it's going to make it think it wraps right around back into the lower addresses and overlaps that application as well. In fact, it's going to think it wraps around back straight onto the same heap. And then we're going to stop that request just shy of our target data. Then we're going to make one third and final request that overlaps our target data, and then we're going to overwrite it, and that will be our arbitrary write. So we're going to take it step by step. And to do this, we're going to need to do things like write non-printing characters, and we want to make this process repeatable. So we're going to use that second Python library that some of you may have installed, called PwnTools. I'm sure a lot of you guys are familiar with this, especially if you CTF. PwnTools is a great little Python framework that is built for like rapid prototyping and exploit development and capture the flag stuff. It's maintained by Zach Riggle, who's ace. And you've got a couple of these Python scripts in this directory down here. We're going to make a copy of the PwnTools template script so that if you guys want to mess with it later, you've got the original, or if you mess something up. So copy that pwntools_template.py script, call it what you want with the exception of pwn.py. People seem drawn to doing that. I sometimes do it. Call it pwn.py. The first thing these scripts do is from pwn import star, and it'll try and import itself, and you'll have a bad day. So I'm going to call mine xpl.py, as you saw there, short for exploit, easy to tab complete. And then what I want you to do is just open up that script in your editor of choice. I'm just going to use Vim to show that you don't need anything special like an IDE to do this or anything, but like Atom, PyCharm, whatever you want. Don't be put off by the amount of text here. Most of this is just either PwnTools boilerplate stuff that you can make it auto-generate for you, and there are a few little helper functions that I've added. For example, like the Malloc helper function here that I'll explain in a moment, that just going to make our lives easier. So this isn't going to be too much of an exercise in writing Python. We're just going to write like 3 lines of Python to exploit this binary. So if you scroll down to the bottom of that script, all we care about is the stuff in between these dashed lines, right? Which right now is just an example of how the script works. So this line starting with log.info just print information to the console. And that one, so basically what this one's getting at is that the heap variable in this script is holding the heap start address. Remember, when we ran this binary, it leaked a libc address and it leaked the heap. So all this PwnTools script does is it's captured that output in a couple of variables so that we can say, like, we can just use the variable heap, and that will be equivalent to the address of the start of the heap. The binary itself is available via the elf symbol. So the elf represents the binary, and we can access symbols from the binary using elf.sim.symbol name. So elf.sim.target is going to give us the address of that target that we want to overwrite, those capital X's in the program's data section. We've also got a Malloc helper function, and that is just a wrapper around option 1 of this binary. So all we have to do is call the Malloc Python function here, and it takes 2 arguments, the size and the data. So what that's going to do, basically, this call here to Malloc is going to pick option 1 from the binary, then it's going to send the value 24 when asked for the size of the chunk, and then it's going to send these 24 capital Ys when asked for data. And the delta function we'll come to shortly. So what I'm going to do is delete everything aside from that call to Malloc. That call to that Malloc helper function, because everything else is kind of logging stuff and examples. And all PwnTools is going to do when we run this script, so you can run it from within Vim using bang./% if you want, or you can just run it from the command line / name of your script, so /xpl in my case. Bang is in what follows is a command / this directory, and % just replaces the buffer name in Vim. And all PwnTools is going to do when it runs is start that binary up, send it the input we told it to, so make that first request, and then it's going to return control to us via an interactive shell. And if you hit return after running the script, you can see that we're basically back talking to the binary, but in like a PwnTools environment instead. And we can see that that first request to Malloc has indeed gone through. But it would be nice if we could actually inspect the heap. All we can see here is the program output, right? We know it requested the chunk, great, but we don't know what the heap looks like. And this is where PwnTools really comes into its own. If you use option 3 to quit, you might have to hit return again. And again, if you're using Vim as well, if you run that script again, at this time with the GDB option, so on the command line, it would be /xpl.py space GDB in all uppercase. What PwnTools will do is do the same thing again, and this time it will attach GDB to the session so that you can debug it. And we get one window with GDB here, and we can, in my case, Alt backtick, depending on your OS. Hopefully, if you have Ubuntu here, you can Alt backtick or Alt tab to the program, and we can see that the program is still running. We can print the target, and if I Alt backtick to the, or I think it's just Command backtick on. It'll be option backtick if you're on a Mac. We can break in Control-C just like we did earlier and issue the viz command. And we can inspect this process's heap as it's running. And as expected, we've got this 2.0 size chunk with the prev in use bit, prev in use flag set. And we filled its user data with 24 capital Ys. And what follows is the top chunk. So if I Control-D or quit back to the editor, anything we add to the end of this line here is going to overflow into the top chunk, at least the next 8 bytes. And what we can do is use PwnTools P64, short for pack64 function, to pack an integer into a string. So that abstracts us away from, having to type all those \x's and stuff like that you're probably used to if you mess with Python, doing a bit of exploit dev. It also means we don't have to remember the endianness. So if we're using addresses here, we can just say pack64 and then just put, hex, whatever the address is that we want, and PwnTools will deal with it, which is kind of nice. It will pack it to the correct length. So what we want is the largest value possible, right? This value here, we're going to send 24 capital Ys, and then whatever we send next is going to overflow into the top chunk size field. So we might as well send the largest value we can, 16 Fs, right? In 64-bit, that's all the bits set. 16 Fs, which just gives us the largest possible top chunk size value. So now Malloc is going to think that top chunk wraps right around the VA space. So once you've done that, you can run your script under GDB again, or with the GDB option, I should say. You can wait for it to start, Control-C to break, and then you can use viz to see that so far our script is doing what we expect. It's requested a hex 2.0 size chunk. It's sent 24 bytes of arbitrary data, in this case just capital Ys, could be anything, to fill up that user data, and then it's sent that packed hex FFFFF value to overflow the top chunk size field. So now, just like earlier, Malloc thinks the top chunk size, the top chunk is huge, and because there are no checks around it. So I can hear someone, was that a question? I'll crack on. All right, so now the next phase is, now that Malloc thinks that top chunk is huge, what we want to do is make that large request. Now, what we want to do is just span the gap between the top chunk, and we want that to wrap right around past the libraries, past the stack, and back around to the binary. And we're going to get away with doing that because Malloc is only going to write to the first and last quad words of this chunk, even though that chunk is going to span a ton of probably read-only and unmapped memory. We'll get away with it unless we try and write too much stuff in between. That's why we're going to make a large request and then a small request, so we don't have to try and ride through all of those millions of bytes of data. So if you close GDB and head back to your editor, what we want to do now is calculate the distance between the top chunk and our target. And this is the leak that you're going to need when you're doing the House of Force. If your target resides on the heap, you don't need a heap leak because, of course, it's relative. It's going to wrap back around onto the same heap. So you don't need a heap leak if you're targeting the heap, but if you're targeting any other part of memory, you're going to need to know the delta between those two locations. So you're going to need to know the address of the top chunk, which is a heap leak, and you're going to need to know the address of your target, which in this case we do because it's a non-position independent binary. So I'm just going to create a distance variable here, and we're going to use that delta helper function that we saw earlier. Delta is just a little helper function that, excuse me, takes two arguments, the start and end address of the start. Basically, it takes two arguments. Sorry, they're like the start of where you want to overlap from and the end address. All it does is do a bit of maths to check that to ensure that we can wrap that value around a 64-bit memory space. Like Python isn't too happy with you kind of trying to do that stuff with regular math. So we want to start from the heap. Remember, our heap variable holds the address of the heap plus hex 20, right? We requested a 20 size chunk, so the top chunk resides at address heap plus hex 20. So and we want the distance between the top chunk and our target. So remember elf.sim to access symbols in the binary, which is non-position independent, so we know their address, dot target. And we want to take hex 20 from that value because, like I said, we want to stop just short. We don't want to have to write millions and millions of bytes. We just want to make a big request that wraps around, stops just shy of our target. Then we can make one small request that overlaps our target neatly and overwrite it. And that'll be our arbitrary write. So once you've got your distance variable set up, so that's delta heap plus hex 20, start of the top chunk, and your destination is elf.sim.target, the target symbol in the binary, take hex 20 off of that to stop just shy. We're just going to make that request. So we are going to use that malloc wrapper function to request distance bytes, and we're just going to send like a single byte of garbage. Once you've done that, run your script with the GDB option. Incidentally, you might have noticed that our heap addresses are a little different. When we first ran this binary under GDB, we could see they were like hex 602000. That's because GDB turns off ASLR. Sometimes that can catch you out, like if you're not familiar with how GDB works, it'll turn off ASLR if you're just debugging stuff that you started under GDB, whereas PwnTools will attach the debugger by default. You can get it to run it under GDB, but the way we're rolling here, PwnTools will attach the debugger, which means ASLR will be in effect, which is nice because we know if we can get this exploit working here, we know it's going to work in production conditions, right? You might notice those addressed a little different. What you can do is pass the no ASLR, so all caps again, so no ASLR, see that in the bottom left, option to your script. So / script name GDB no ASLR. That will disable ASLR for the sake of debugging. So now what we can do is we can option backtick to the binary. We can see that we've made 2 requests. The binary is still working, which is nice. And we can alt backtick back to GDB, Control C to break. And this time, don't use the viz command. Pwnbag will have a write meltdown. There's a very, very, very large chunk on the heap. Instead, what we're going to do is use the dump quad command to dump quad at target -16. And here we can see in the bottom left, our target, those capital X's, those hex 58 bytes. And this time there's a rogue value, right up here. And what we can do is confirm what that is by using the top_chunk command, which is a pwnbag command, which gives us the address where Malloc thinks this heap's top chunk resides, hex 602000, right here. So you can see we've scrubbed a lot of size off of that top chunk. This used to be all the F's. This was the largest possible 64-bit integer, and now it just sits at hex 1019. So we've scrubbed a lot of size off it, wrapping right around that 64-bit address space, but we have successfully done it, right? So now the next request that we make, we know that Malloc is going to break another chunk off of this top chunk, and the first quad word of its user data will neatly overlap with our target data. And we can do that manually. If you just continue in GDB, alt backtick back to the binary, make a third request. I'm just going to go for a minimum size chunk this time, and then type any old data in there. when we use the target option to print that target data, we can see that instead of those capital X's, it prints my data instead, that much win string. And that's our arbitrary right. That's all there is to the house of force when it comes to turning it into an arbitrary right. So all we really did was leverage the overflow, the heap overflow in this binary, to overwrite the top chunk size field with a large value, right? That's what our first Pwn Tools line did here. Then we calculated the distance between the top chunk and our target data. We made a very large request from Malloc that, because we've tampered with that top chunk size field, it was able to make. Otherwise, it would, just behave by the rules and it would request memory at the appropriate location. That request wrapped, or that chunk, I should say, wrapped right around the VA space, stopping just shy of our target data. And then we can add that last request to our script like this, if you want. So one last request for a minimum size chunk, and then we can run our script without the GDB and no ASLR options, so under production conditions, to make sure that it actually works. And then we can hit option 2 and see that we have overwritten our target data. So that's how we leverage the house of force technique for an arbitrary right. The house of force part is essentially the bit where we overwrote the top chunk size field with a large value, and then just made a very, very large request to span that gap between the top chunk and whatever bit of memory we wanted to hit. And of course, we've made an arbitrary right here. We could have just made any old request and made the program segfault if we wanted a denial of service. We potentially could have overlapped that third chunk with some important data we wanted to read, for example. Just in this case, we're going for an arbitrary right because it's a nice strong primitive to work on. How's everyone doing?
All good, mate.
All good? I sent a few bits and pieces in the chat.
Well, I've got a question if you're ready for a question.
Yeah, go for it, and then we'll wrap things up.
Okay. So obviously, when it comes to overflows, I'm familiar with Stack Overflows. You have your buffer of how many characters, you control EIP, you get rid of your bad characters, and you can put your shellcode in there. Not so familiar with heap overflows. Is there sort of like a similar mapping, forgive my ignorance, where we can write shellcode into this arbitrary bit? So you've gone through your levering your top chunk, you've got your delta, you've done your wraparound, you've got to your request, you've overwritten with arbitrary stuff. Can we now get remote code execution by putting some shellcode in there now?
Good question. We can't do shellcode because this is we've seen this NX, right? So we could try and write shellcode to like the heap or the stack or whatever, but we're never going to be able to execute it. But what we'll do next, if everyone's happy with it, is get arbitrary code execution. Okay. So as you've seen, we're able to, let me remove a pet. Again, so we know that we can make an arbitrary right, and since we've got all of these, since we've leaked, like, the address of the heap and libc and all that good stuff, we could potentially just target this arbitrary right anywhere we like. Yeah. So let's consider like what we might target with our arbitrary right to get code execution. We know there's NX, so we can't go trying to write some shell code anywhere and then point execution to it because it won't run. But what we can do potentially is, okay, so we could target the stack, for example. Let's think about this in terms of ASLR zones. We could target the stack. Stack has a bunch of cool stuff on it, return addresses being one particularly useful thing. In this case, that's not going to work because we haven't got a stack leak and the binary is subject to ASLR, so we don't know where the stack is. We could target the heap itself. Like I said, we could just wrap around back onto the same heap and we wouldn't even need a leak if we did that. That might work if you have, again, like function pointers or whatever on the heap, for example. In this case, we don't. The only thing on the heap in this case is our own data. But again, you could potentially target sensitive data on the heap. We could target the binary, like I said, got PLT sections, FINI array sections, get you code execution when functions are called or when the program exits. But you'll recall this program was compiled with full railrow, so we can't overwrite those vulnerable sections, those useful sections, I should say, in the binary itself. So that just leaves libc in this case. There aren't any other libraries in play except for the dynamic loader. So libc, oddly enough, actually has a got.plt section of its own, although sometimes functions can be a little hard to call from that. It has things like exit funcs and gosh, what's the other one? Exit funcs and TLS detours as well. So when things are getting torn down, you can potentially get code execution there in the same way as you do FiniArray. But more recent versions of libc use something called pointer mangle to protect those pointers. So we'd need like an arbitrary read. We'd need like an arbitrary read first to read them to get like the secret key that it's using to that to encrypt those little values. So it's you know, we're actually pretty limited in this binary in what we can attack, you know, because of the full railroad, because of the NX. However, there is a heap specific way to get code execution. And I'm talking about the malloc hooks. Every one of Malloc's core functions, like malloc, free, realloc, and a few others, has an associated hook. And that hook just takes the form of essentially a function pointer in libc's data section, right? And they're most often used for like initialization. Programmers can use them to implement like their own memory management systems. You can use them to collect like malloc statistics and stuff, but we're going to use these hooks to get a shell. So what we're going to do is remove everything after distance. And in fact, I'll tell you what, let's just remove the one line after distance. So we're going to keep that first line in our script, right? We're going to get code execution using these malloc hooks, and I'll explain a bit more about how they work in a moment. So we're going to keep that first line. That's our house of force primitive, right? So that's overwriting, that's leveraging the overflow to overwrite that top chunk size field so that we can actually make an arbitrary write. Now we're just going to use that arbitrary write to get code execution. We have a libc leak, so we're going to target libc. And this time, the distance is going to be the, we're not going to use the delta function because we're not wrapping around. Recall that libc sits after the heap. So we're just going to overflow straight from the heap. Or not going to overflow, I suppose, but we're going to make a large request that spans the gap between the top chunk on the heap and the libc data section, which we've been able to leak. You couldn't just do this without a libc leak. So what we want is libc.sim. So libc represents the libc binary in this case. libc.sim, and the address of the malloc hook, the symbol for the malloc hook is __malloc_hook. Again, if you are following along, I am going a little bit fast. I apologize for that, but I'm very aware that it's only lunchtime in the States and it's your evening in the UK. So I'm trying to keep things brief. So that is the malloc hook, and we want to do the same thing basically. We want that delta between our target, which this time is the malloc hook rather than the string of x's in our binary. And again, we want to take hex 20 from that to stop just shy. And we want the difference between that and again the top chunk. So heap plus hex 20. And then we're going to make that same request again. This time we are going to just comment out that last request to malloc. So doing exactly what we did before, overwriting the top chunk size field using our overflow, setting it to a large value, making a large request that malloc otherwise couldn't make, spanning the gap between the top chunk and our target. This time our target is in the libc data section, and it is the malloc hook. Okay, so we're going to run our script like we did before with the GDB and no ASLR options. All seems well. We're going to break again, don't use viz. We are going to do the same thing that we did before to our target to inspect memory before it. We're going to dump quad, and then remember that malloc hook symbol is malloc __malloc _hook, and GDB does pointer math on our behalf, so we're going to use -2. I apologize, we're going to need to put an ampersand at the beginning of that that symbol name as well. So that makes this value here, this GD0C10 address, that's the malloc hook, right? So, like I said, the malloc hooks essentially take the form of function pointers. And throughout the normal operation of a program, with the exception of initialization, they'll be null like they are here. When a particular malloc hook is null, as I said, this is the malloc hook. I know I keep saying malloc hooks and the malloc hook, but there's the free hook, the realloc hook. When a particular function's hook is null, so in this case, this is the malloc hook, calls to malloc are put through straight to the malloc function itself, right? It's essentially ignored when it's null. But as soon as we write a value over the malloc hook, then all calls to malloc will be redirected to whatever address we put there. And as I said, this is used normally for initialization. It's used for implementing your own memory managers like jmalloc or jmalloc, or collecting malloc statistics and stuff. And there are a few bits and pieces of libc that have hooks for this purpose. And these hooks remain writable for the entire duration, for the entire lifetime of the program, even if full railrow is employed, which makes them a really nice target for heap exploitation. All you have to do is overwrite, say, the malloc hook with the address that you want to point execution to, and then call malloc. You even get an argument because you have to pass your size to it. So if we use the top_chunk command again, we can see that this dd0c00 address here is the top chunk, making this the top chunk size field. Again, we're set up so that the next request we make from malloc will give us a chunk that comes off of this top chunk and aligns the first quad word of its user data perfectly with the malloc hook. You can see we've scrubbed a lot less size off of this one this time as well. We've still got like a few Fs here. That's because the distance between the heap's top chunk and the libraries is much smaller than the whole wraparound distance between the heap and our target data. So we're just going to do a test. What we're going to do is uncomment that last line, and we're going to make this last request here. That's the first quad word of which we know is going to overwrite the malloc hook. And we're going to use PwnTools pack64 function to write the value deadbeef in there, right? So 32-bit value, but pack64 will pack that to the appropriate length, put it in the appropriate endianness, and hopefully that will overwrite the malloc hook. And deadbeef is going to be an unmapped value, basically. This is a nice way, if you're unfamiliar with it, of just giving like a guaranteed unmapped value, and then when you try and redirect execution to it, your program will crash. And then if you can see your instruction pointer points to that controlled value, you know you're on for a winner. So if we run this again and the program continues to run, if we tick back to the program, hit return to print the menu, you can see that we've used 3 of our 4 requests, so we get 1 more. Again, it's just an arbitrary value to sort of funnel students normally down like a particular way of exploiting it. Often in a regular program, you might be able to make as many requests as you like potentially. And I'm just going to make an arbitrary sized request. I can request 0 bytes, for example. And this time we're not prompted for data. The program has hanged. And we can backtick to the program where we can see that we have indeed stopped at the address deadbeef. Our instruction pointer holds the value deadbeef. So we can use our DQ command to see that the malloc hook, in fact, we can just print __malloc _hook to see that its value has been overwritten with deadbeef. So we're able to use our house of force primitive to overwrite the malloc hook. And this is that really nice synergy between like heap exploitation and getting code execution with heap exploitation. Is that you can target the malloc hooks and you're still staying within the heap implementation to get this code execution. So all of the binaries that I use to teach this stuff, for example, only have 1 bug. They only ever have 1 bug. Some of them are a single byte overwrite. Some of them are a single null byte overwrite. One of them doesn't have any bugs at all in it and relies on a bug in the glibc implementation, and you can still get code execution with it. So that's what I really like about heap exploitation, is that it's very much, you don't necessarily need all these different bugs to come together to make it work. You might do, but not necessarily. So all we need to know now is, where do we want to send execution? Again, we have a libc leak, and for the sake of time, I'll tell you what our plan is. We're going to swap out that deadbeef value for the address of libc's system function. You guys are probably familiar with that. If I change that to libc.sim.system, for example, we can see the man page for that says that basically it's going to do the equivalent of execl bin shell, so it's going to run a shell, and then it's going to pass our command into it. So all system does is it takes a single argument, dead simple function, and it takes a pointer to a string, and that string is interpreted as a shell command, basically. So we could do, system ls. System bin shell is obviously the classic way to get a shell, right? So if we can redirect execution to the system function and pass it the string bin shell, pass it a pointer to the string bin shell, like /bin/sh, as in sh, the shell, we can get code execution. We can get a shell, basically. And that's exactly what we're going to do. So by overwriting the malloc hook with the address of libc's system function, we are in effect forwarding all future calls to malloc to the system function. And the great thing about that is that system takes one function, one argument, malloc takes one argument. So what we can do is masquerade our size request. In this case, we're lucky we can make arbitrarily large requests. That might not always be the case, but we can masquerade the size argument that we're passing to malloc as a, or I should say, we can use the we can masquerade the address of the string binsher as a size argument and then pass it to malloc. Because we've overwritten the malloc hook, all future calls to malloc will be forwarded to the system function, and it will pass it the same argument, except this time it won't be a size, it will be interpreted as the address of a string, and then that will become the equivalent of system, hopefully, binsher. And there are a couple of ways we can do this. Because we have a heap leak, we can stash data on the heap. So what we can do is, for example, instead of this single X that we made, single X that we wrote into memory, single byte of garbage data that we wrote into memory using our large request, we can just type the string binsher, don't forget to null terminate it. And then we can make one final request to malloc with the address of the heap plus hex 30 as the size value. It doesn't matter what argument we pass to the second request for data, because it won't even get that far. We'll have got a shell by then. So to clarify, what we're doing here is we've used our house of force primitive to overwrite the to make an arbitrary write, basically. And then instead of overwriting our little string in the target's data in the program's data section, we've overwritten the malloc hook in libc. There's a free hook, like a realloc hook. You know, we can target any of malloc's functions, but this program only calls malloc, or that's the only function we control. We've overwritten that with a pointer to libc's system function. So the next time we call malloc after that's happened, it will become the equivalent of a call to system. So the last thing we're going to do, like I said, is make a call to malloc, and as the size field, we're going to just send it the address of the string binsher that we've written onto the heap earlier in line 44 here. And that should become the equivalent of system binsher. Again, we're only able to do this because we know the address of our string on the heap. We might, if we didn't have a heap leak, maybe we could find, maybe we were able to write it into the binary, which is non-pick, etc. So let's run this under production conditions without any, without the GDB and no ASLR options to make sure it works under ASLR. And there's our shell. Like I said, those calls to malloc are being forwarded to system. You could forward them anywhere you like, into a piece of the program that authenticates you as an administrator, for example. In this case, we just want a shell, so we send it to system, which we needed a libc leak for. So the other option for finding a string is, oddly enough, libc actually has the string binsher in it. You'll recall that if we go to the man page for system again, it calls xxl binsher, which means that string must exist somewhere in the libc binary, right? So since we have a heap leak, since we have a libc leak, and we're familiar with this particular version of libc, we can instead do something along the lines of next bracket libc.search. This is just Pwn Tool stuff, basically. All I'm doing is finding the string binsher within the libc binary object, that shared object. And once you've done that, so like next libc.search, again, that's just Pwn Tool stuff for finding that string within libc. Oh yeah, because it's Python 3, we need to append a lowercase b to the beginning of that string. And then again, we can get a shell that way. So there's that script. If you guys, if I was going way too fast, or you guys, if your script had some problems with it, there are these Pwn Tools _solution, Pwn Tools _solution target and shell scripts. The target just makes that arbitrary write, overwrites the target. So you can run that and press return and see that it's overwritten the target. And then you can run the Pwn Tools solution shell script as well, and that'll get a shell in one of those two ways as well. And they're both commented, so you can kind of use them to refresh your memory as well. And on top of that, you've also got the that heap exploitation heap lab PDF bits and pieces as well. So I know I've really dragged that out, guys, but I hope you enjoyed it. Let's wrap things up with any questions.